Hello everyone, and welcome to today's webcast on Geospatial Analytics on Databricks Lakehouse. My name is Apoorv Tandon, and I am a data and AI consultant for Thorogood, based in our London office. I will start with a short introduction about Thorogood and who we are, then set the stage for what geospatial data is, what geospatial trends we are seeing in the data and analytics industry, common geospatial file types and libraries, and then introducing Databricks Mosaic library for Spark-enabled geospatial analytics. Then I will do a demonstration of some of the key features of three geospatial libraries, namely GeoPandas, Raster.io, and Databricks Mosaic. Then introduce the Geospatial Lakehouse approach for doing geospatial data analytics at scale, give an overview of an insurance use case that we recently worked on using geospatial data to then summarize how Thorogood can help you get started. We are an independent professional services and consulting firm specializing in data and AI solutions. We operate as a single organization serving our customers globally, working in leverage teams across our offices in London, Philadelphia, Boston, Bangalore, Singapore, and Sao Paulo. We provide a full range of services to support business goals. This includes, but is not limited to, covering the end-to-end life cycle of any project, from initial strategy and roadmap definitions, gathering requirements, designing and implementing complex systems, and training and supporting business users. In terms of technologies we work with, we are an independent consulting firm, meaning we don't work with one specific technology. We do, however, work and partner with many of the key players in the market in order to provide our clients with the best solution that suits their needs. So, I thought I would start by sharing some of the headline numbers. As per a study published in geospatialworld.net, the geospatial market is forecasted to be $681 billion in 2025 and is estimated to pick up a much faster pace post 2025 on the backbone of more technology innovation, integration of workflows, and augmentation of spatial analytics in business processes. So, it's going to be a big market, and organizations can gain significant competitive advantage. So, what is geospatial data? Geodata is the data that includes information related to locations on the Earth's surface. It combines location information, usually coordinates on the Earth, with characteristics or attributes of other business data sets over a given period. The data comes in two main formats: raster data and vector data. The vector data represents features as discrete objects, points, lines, polygons, and each feature has associated attributes like population, name. Raster data represents data as a grid of pixels. Each cell stores a single value like elevation, temperature, land cover. Vector data has accurate representation of features, supports spatial relationships, and has a rich association with each feature, but requires more space than raster data. Whereas raster data compresses well and is suitable for large data sets and ideal for representing continuous phenomena like temperature gradients. For raster file, choosing an appropriate grid size is critical based on use case and accuracy requirements. Vector data is generally stored as a shapefile or GeoJSON formats, and raster data is stored as GeoTIFFs or other image files like ERDAS, Earth Resources Data Analysis System. There are geospatial data use cases in almost all industries. I've highlighted a couple here. I will not go in detail for each one, but just highlighting 3-4 for now. Property risk assessment, knowing a building's size, shape, location, purpose, and occupancy helps insurers estimate how unsafe it or its tenants are to an accident. Fraud detection. Uber has used geospatial data to identify driver fraud. A common scamming technique involves GPS spoofing apps. In this case, driver would use two phones, one with a driver app and another with a passenger app, with fake credit card details assigned to it. The scammer would accept a new ride from fake account and pretend moving. Uber has over 600 different red flags as warning against such scams. Mapping and navigation. Geospatial data is used in web-based navigation maps. These maps are updated regularly based on geospatial data and are widely used in everyday life, like Google Maps. Consumer insights. Geodata can be used to identify underserved areas where demand for specific towers or services exist. As with tabular data, there are common terminologies like header, primary key, foreign key, and we perform common operations like filtering, pivoting, joining tables, and algebraic operations. Geospatial data too have some terminologies like coordinate reference system, which is a framework that defines how coordinates, latitude, longitude, are onto a two-dimensional surface, and georeferencing, which is the process of assigning specific coordinate reference system. Some of the common operations include resampling, which is to change the resolution of a raster file, clipping, which is to extract a subset of spatial data that falls within a specified boundary, masking, which is to apply a mask to a raster data to include or exclude certain areas based on a specified condition. The geospatial domain is fast moving at the moment with a wide range of libraries that help with vector and raster data, allowing us to perform the required operations. I will not cover all of them now, so highlighting a few popular ones here. GeoPandas. It extends the functionality of pandas to perform data analysis and manipulation of vector data. Common applications include reading GeoJSON file, performing spatial operations, and visualizing the data. Raster IO. Raster IO allows you to read raster files, generally in GeoTIFF formats, performing operations like masking, clipping, reprojections, and then saving the modified files. I will be showing some of the common operations using these two libraries in my demo too. Other libraries are RioXarray, which is built on top of raster IO and contains a wider range of mathematical operations for raster data. Apache Sedona, which provides spatial extensions to Apache Spark for large-scale spatial operations. Another library which is getting really popular is Databricks Mosaic, which is an extension to the Apache Spark framework, allowing easy and fast processing of very large geospatial datasets. With capabilities for ingestion, transformation, visualization, and machine learning integration, Mosaic facilitates scalable geospatial analysis. Its distributed computing approach can efficiently handle vast datasets, supporting various formats and integrating seamlessly with other Databricks components, promising streamlined spatial workflows for data scientists, analysts, and data engineers, hence naturally fitting the library of choice for geospatial lakehouse pattern that I will be covering later in the session. But enough of me talking about it. Let's see how some of it works. In the first use case, we will try to perform exploratory data analytics on geospatial data. During the demo, we will explore spatial operations like reading GeoJSON files, perform spatial joins, and visualizing using GeoPandas, while also leverage raster IO for reading GeoTIFF file, extracting band information from the TIFF file, and conducting advanced algebraic operations like NDVI calculation. In the second use case, as a geospatial analyst, I would like to combine two open source datasets like New York Taxi and New York Precinct geometry file using Databricks Mosaic library and H3 indexing to plot the density map revealing taxi activity hotspots. I will be leveraging Databricks tool for this. So let's head to it. This is the landing page of Databricks. Databricks is a unified platform for machine learning, data engineering, and SQL analytics. And we can see various operations pertaining to each of them in the left panel. In Databricks, we write code in a place called notebooks. We can use multiple languages to write our code. I am using Python in my case. And I also acknowledge the fact not everyone knows Python and neither will I be going through the code line by line. My aim for today is to just showcase code to show high-level common operations to prove the concept. The first notebook that I'll be using is called Exploratory Data Analysis of Geospatial Data using Databricks. This notebook will explore various geospatial operations with GeoPandas and raster.io library. Common functions include reading GeoJSON, GeoTIFF files, performing data transformation and algebraic operation, and then visualizing the result. I've also created Markdown to provide some commentary in my notebook using this magic %MD command. Now, I'm importing the GeoPandas library as GPD. Then I'm reading a GeoJSON file named Netherlands.geojson using gpd.read command and creating a Netherlands geodata frame. GeoJSON is an open standard geospatial format that represents geographic features and their non-spatial attributes. Now I'm querying the rows using geodataframe.head command. The file has a single row of data with a geometry column. So here we can see that it's a polygon. Then I can print the coordinate reference system of the file using geodataframe.crs command and then visualizing the results using the geodataframe.plot command. And here we can see the shape of Netherlands. In this activity, I'll be joining two GeoJSON files, Earth data with country coordinates and United States National Forest cover, and then plot the forest cover per square kilometers for US. So first, I'm reading my first file, which is the Earth dataset using gpd.read file command. It has geometrical shapes for each country. And then I'm visualizing the geodata frame colored by the continent column. Now I'm reading my second dataset, which is the US National Forest cover data, again a GeoJSON file, and then performing a spatial inner join between the two datasets using the sjoin command and using the predicate clause within, and then plotting the resultant dataset to show the forest cover per square kilometer. Here, darker the color on the chart, higher the forest cover per square kilometer and vice versa. Now let's look at the second library, which is raster.io. So raster.io allows you to read raster files, which are generally in GeoTIFF format. A GeoTIFF file is a raster image format that incorporates geographic information such as location coordinates and projection data. Now I'm importing the raster.io library as RIO. For this, I will be using a small stat TIFF file, and then I'm trying to read it using the rio.open command. Using the .metadata command, I'm trying to see what's the coordinate reference system of my file along with height, width, and the count of bands. A band refers to layers of data representing different spectral bands such as red, green, blue, captured by remote sensing instruments in satellites. Now, I'm trying to read those individual layers, red, green, blue, and near infrared using .read command and visualizing the results using .show command. Here we can see the plot of images for red channel, green channel, blue and near infrared channel. Now I'm performing the normalized difference vegetation index NDVI algebraic calculation by extracting two bands, near infrared and red, and performing NIR minus red divided by NIR plus red operation. NDVI is used to quantify the density of vegetation using the spectral data collected from satellites. And then I am plotting it, and you can see the image, the green portions of the chart, the vegetation density. So to summarize, in this notebook, we read the GeoJSON and GeoTIFF files using GeoPandas and raster.io library respectively, performed data transformations like spatial joins between the two datasets and visualized the results, and performed algebraic operations like NDVI, which is normalized difference vegetation index, which is used by insurance and business industry to perform risk assessments for loans in rural areas or as a monitoring tool for urban development and natural disaster predictions. Now, let me head to my second notebook, which is called Databricks Mosaic Notebook. In this notebook, we will explore the Databricks Mosaic library by combining two open source datasets, New York Taxi and New York Precinct Shapefile. These datasets will be individually read, processed, and geospatially indexed using H3. The objective is to generate a density map showing what precinct areas had the most taxi activity throughout the year. The visualizations within this demonstration will be handled by Mosaic Kepler. Again, here I've provided some commentary by creating a markdown using the %MD magic command. Then I'm importing the Mosaic library as MOS, reading the first file, which is the precinct data file, using spark.read.format command. My file has a geometry column, and also I'm creating H3 indexes by creating a Mosaic index column using mos.grid tessellate explode command. And then when I display it, I can see my geometry column and the index column that I've created for my precinct file. And then I'm using Mosaic Kepler to plot the New York precinct shape that has been reshaped by creating these hexagonal H3 indexes. Then I am now reading my second dataset, which is the New York taxi file, and then performing the data transformations to derive a geometry column from the longitude and latitude which are present in this dataset. Also, please note all the operations using Databricks Mosaic are Spark enabled. So we can see these Spark jobs that have started running, which means all the operations are getting distributed to multiple worker nodes for distributed computing to form the basis of geospatial data analysis at scale. Once the transformations are done, if I display the resultant data frame, I can see my geometry column, which is a point file which has been created from longitudes and latitudes. And then I'm again using Mosaic Kepler to visualize the taxi activity, again as these hexagonal H3 indexes. Here, yellow color represents the highest activity, followed by orange for New York. And then I'm performing the group by and aggregation to calculate the density, then joining the two data sets using the dot join command, and then again using Mosaic Kepler to visualize the taxi hotspots for various H3 index precinct areas. Here, purple color shows the highest density, followed by the red areas. So to summarize, in this notebook, we read, processed, and geo-indexed the two data sets using Databricks Mosaic, generated a density map, and visualized the results using interactive Kepler library. Databricks Mosaic enables Spark-centric distributed computing for handling large datasets, bringing in performance and scalability to design geospatial-related architectures. So this was a quick demo of some of the common operations. And now let me head back to my slides. Now let's look at Geospatial Lakehouse pattern to enable geospatial analytics at scale. In this pattern, we are suggesting something like this as an high-level architecture. From the left, a bronze layer is where all the data is landed and our master data is maintained. We've performed some common pre-alignment operations like reposition on our base files and stored them in a bronze stage layer. Then the silver layer is really where we are aligning all the data to a common grid system and performing specific calculations like NDVI scores, and then finally merging the outputs in the gold layer before they can move into a semantic database. As an example, I've drawn out what data layering could look like within the lakehouse if we take two models as an example. The bronze layer on the left is having the raw raster data and the required config files. User-defined functions are created for common operations that can be leveraged across the models. The silver layer stores the common master data that could be utilized across models along with country-wise model-specific calculation results. And then model-specific outputs are combined in the gold level. Geospatial master data can be combined with other master data like class of business, calendar to enhance further analysis. To support Lakehouse, one needs to look at a few other considerations too. Again, I will not cover all of them here, but to highlight a few, aligning master data to a common base index like H3 across projects, creating workflows to automate and orchestrate the execution of logical tasks. Tools like Databricks enable teams to move away from executing code locally to cloud. This in turn helps specifying compute power based on the task at hand. Having specialized size compute as a large cluster will be required for large raster files and small for small, maintaining a few range of clusters with configuration files to run a specific set of countries on the large cluster or a small cluster could speed up operations and save costs. And then maintaining a functional library to perform certain common operations could be beneficial across teams, making it easier to update a version as libraries evolve. Along with that, maintaining common naming conventions could help reusability and simplifying ease of use. I also thought to highlight a model optimization use case that we worked on recently for an insurance company. The company had a fire model that dynamically determines the area of interest, then crops master data files for elevation and tree cover, and then conducts 80,000 simulations per country to predict the probability of fire. The model was being run sequentially as shown in the block diagram on the left. Following the Lakehouse approach, we set up configuration files, user-defined functions, created workflows and notebooks in Databricks to parallelly execute some of the independent operations as shown in block diagram on the right, which provided 3.4 times faster predictions and ease of maintenance. Just to summarize, we started off the webcast by talking about the geospatial market trends, what geospatial data is, along with some popular libraries and tools to enable the analysis. At the center of this is the Lakehouse vision, an ecosystem that makes it easier for us to manage data and gain more insights from it. This forms the basis of geospatial data analysis at scale. Of course, we can't consider technology as the silver bullet. We need to put the right data into it and have the right processes and people to build it out. But we've seen a lot of value across all industries, be it consumer goods or financial services. And if you think back to the numbers I shared at the start, the potential value is immense. Here, I have highlighted some of the building blocks in setting up the Lakehouse foundations. These include documenting and sharing the common geospatial standards, building a common repository of master data files that could be used across the organization, create a library of common user-defined functions that could be used across the projects to help modularize the code, creating geospatial compute that helps teams move away from running code on local machines. Taking actions is key, and shown here is the path which we've used to help a lot of organizations progress on their geospatial journeys. The approach works by identifying the best opportunity, then running a workshop, to then developing solutions. So, if any of this is of interest, please feel free to reach us. Thank you all very much for joining and have a nice day.